There is a black hole at the edge of the observable universe that weighs more than 50 million suns. It does not sit at the center of a massive ancient galaxy built over billions of years. It does not have the deep stellar history that every model of cosmic evolution says it should have. What surrounds it is almost nothing, a thin, barely assembled collection of gas and a handful of young stars that together weigh half as much as the black hole itself. By every rule we have spent decades building into our understanding of how the universe works, this object should be impossible. And yet the James Webb Space Telescope found it, measured it, confirmed it, and handed the scientific community a problem that no existing explanation fully solves. We are going to follow this discovery from the moment Just caught the signal all the way back through 13 billion years of cosmic history to the first fraction of a second after everything began. We will look at what the standard model of galaxy formation actually predicts, why this object breaks it, and what the leading theories say about how something this massive could have existed this early. Along the way, we will get in primordial black holes, the first stars, the long dark silence before any light existed, and the physics of how a telescope built by human hands can read the chemistry of an object older than our planet by nearly 3 times over. Make no mistake about what this video promises. By the time we finish, you will understand not just what Just found, but what it means for the entire history of the cosmos. The answer changes the order of operations. It moves something from the end of the story to the very beginning. And when you understand that shift, the universe looks different than it did before. The James Webb Space Telescope was not pointed at empty space when it found this object. It was pointed at one of the most studied regions in the sky, a dense region of thousands of galaxies known as Pandora's cluster, sitting roughly 3.5 billion light-years from Earth. This cluster is not famous for what is inside it. It is famous for what it lets astronomers see behind it. Here is why that distinction matters. A massive collection of galaxies, gas, and dark matter bends the fabric of space around it. Light from objects far behind the cluster does not travel through it in a straight line. Instead, the light curves around the concentrated mass, following the warped geometry of space that the cluster creates. When it arrives at a telescope, it has been stretched, brightened, and sometimes split into multiple copies. Scientists call it gravitational lensing, and they have used it deliberately for decades as a way to extend the effective reach of their instruments. The universe provides a free optical boost, and astronomers plan observations specifically to take advantage of it. In the case of the target we are discussing, the lensing effect from Pandora's cluster split the light into 3 distinct images, 3 separate copies of the same source appearing at slightly different positions in the telescope's field of view. Researchers identified all 3 as the same object by matching their spectral fingerprints. Each copy had traveled a slightly different path around the cluster, but all 3 originated from the same source. That source, when researchers traced the light back and measured how much the universe had stretched its wavelengths during transit, turned out to be 13 billion light-years away. The light left its origin when the universe was only 700 million years old. That is roughly 5% of its current age. The working designation for this object is Able 2744 QSO1. For the purposes of this discussion, we will simply call it QSO1. When the team analysed the spectral data, the first number that came back was the mass of the central black hole, 50 million solar masses. That figure was not a rough estimate. It was derived through a technique called broadline analysis, which reads the width of specific emission lines in the spectrum to calculate the speed of gas orbiting the black hole, and from that speed works backward to determine the gravitational mass at the center. The method is well calibrated against black holes in galaxies close enough to verify independently. The results stood. Then they measured the stellar mass of the surrounding galaxy. 25 million solar masses. The black hole outweighs everything around it by a factor of 2. That ratio is what broke the model. In every confirmed mature galaxy ever studied, the central black hole accounts for a tiny fraction of the total stellar mass. The Milky Way's central black hole, confirmed through decades of tracking stellar orbits around the galactic center, weighs 4 million solar masses. The rest of our galaxy contains somewhere between 200 and 400 billion solar masses of stars. The black hole is a rounding error. It is a detail buried inside an enormous system. The galaxy is the story. The black hole is a footnote at the center. In QS01, the footnote is the only chapter. The galaxy barely exists. The black hole is the entire system. Astronomers have a term for this kind of configuration. They call it a naked black hole. A black hole so gravitationally dominant at such an early stage that the galaxy forming around it never had the time, the conditions, or possibly the freedom to grow. It is a system where the center arrived before the edges, where the densest and most extreme object formed before the structure that normally produces and surrounds such objects. Before we get into how this could have happened, and we will get there in detail, it helps to understand exactly how wrong this is according to everything we built the half-century of cosmology on. The model of galaxy formation that QS01 violates is not a rough sketch. It is a framework assembled from thousands of observations, refined through generations of telescopes, and backed by physics tested at every scale from laboratory experiments to the cosmic microwave background. To understand what broke, you first have to understand what was standing. After the Big Bang, the universe expanded and cooled through a specific sequence of events. Protons and neutrons locked together into atomic nuclei within the first 3 minutes, a process called Big Bang nucleosynthesis. For the next 380,000 years, the universe remained a dense, opaque fog of charged particles. Free electrons scattered light in every direction the way fog scatters a headlight beam. Light could not travel in a straight line. The universe glowed, but was completely opaque. Then, at roughly 380,000 years post-Big Bang, the universe cooled enough for electrons to combine with nuclei and form neutral atoms. Suddenly, light had room to travel. The fog cleared. The universe became transparent. The radiation released at that moment still reaches us today in every direction as the cosmic microwave background, the oldest light we can detect, a perfect record of what the universe looked like at that first moment of clarity. After that, the universe went dark again, not because anything blocked the light, but because there were no light sources, no stars, no galaxies, no nuclear furnaces of any kind. Just vast, slow-moving clouds of hydrogen and helium gas, organized slightly unevenly because the Big Bang itself was not perfectly smooth. Quantum fluctuations in the earliest fraction of a second had imprinted small density differences into the fabric of the universe. Regions that were fractionally denser began pulling in surrounding gas. Regions that were fractionally emptier grew more empty over time. These density variations grew slowly under gravity, seeding the large-scale cosmic web of filaments and voids that organizes every galaxy we see today. The structure was invisible during the Dark Ages, but it was building. Dark matter dominated this early phase of structure formation. Ordinary hydrogen and helium gas could not cool and collapse efficiently on its own in the conditions of the early universe. Dark matter, which interacts through gravity but not through electromagnetic force, had already begun organizing into gravitational halos during the Dark Ages, forming the invisible scaffolding into which ordinary matter later fell. This is confirmed by detailed comparisons between observations of the modern universe and cosmological simulations. The large-scale structure of galaxy clusters, filaments and voids matches simulations only when dark matter is included. Without it, the models fail. As dark matter halos deepened their gravitational wells, hydrogen gas fell in. Inside those wells, gravity compressed the gas. Compressed gas heated up. Eventually, in the densest regions, the conditions for nuclear fusion were met. The first stars ignited. These first stars were enormous by modern standards. Scientists call them population 3 stars. They formed from gas that contained only hydrogen, helium, and trace amounts of lithium because those were the only elements the Big Bang produced directly. Heavier elements, everything from carbon upward in the periodic table, are created inside stars and only dispersed into the wider universe when those stars die. The first generation of stars had no heavy elements available to them, which affected how they collapsed. Without the cooling that heavy elements provide in later star formation, gas clouds in the early universe had to compress to higher densities and temperatures before fusion could begin. The result was stars far more massive than anything that regularly forms today, possibly hundreds of times the mass of the Sun. These stars burned intensely. They lived for only a few million years before exploding as supernovae, seeding the surrounding medium with the first heavy elements. The ultraviolet radiation they produced while alive ionized the surrounding hydrogen gas, gradually clearing the neutral fog that had persisted since the end of the Dark Ages. This transition from a neutral hydrogen universe to an ionized one is called the epoch of reionization, and it happened over several 100 million years as the first stars and early galaxies burned through the surrounding fog. QS01's light left its source right in the middle of this period. The universe at that moment was still partially opaque, still mid-process in clearing the neutral hydrogen between galaxies. Inside these first galaxies forming during reionization, the Standard Model says this is when central black holes began to grow. Material piled up at the centers of galaxies. Gas that lost angular momentum spiraled inward. Black holes formed from the most massive stars, then grew slowly by consuming surrounding gas and occasionally merging with other black holes during galaxy collisions. Over billions of years, this incremental process built up the supermassive black holes we find at the centers of mature galaxies today. The relationship between black hole mass and galaxy mass in all those mature systems turned out to be surprisingly tight. Across hundreds of confirmed galaxies, researchers found that the mass of the central black hole tracked a fixed proportion of the mass of the galaxy's central stellar bulge. The bigger the galaxy, the bigger the black hole, in a ratio that held across a remarkable range of galaxy sizes. This relationship, known as the M-sigma relation after the velocity dispersion measurement used to derive it, was published and confirmed across the broader astronomical community. It became foundational. It suggested a deep, tightly coupled coevolution between galaxies and their central black holes, each shaping the other through a feedback process that somehow always converged to the same ratio. Textbooks incorporated it, graduate courses taught it. Review papers cited it as background contexts rather than something that required defending. It was settled science. QS01 does not fit on that relation. The ratio is inverted. The black hole is twice as massive as its host galaxy. If you plotted QS01 on the graph that shows the M-sigma relation for hundreds of other galaxies, it would not scatter slightly off the trend line. It would land in a completely different region of the plot, in a location the relation says should be empty. This is not a marginal deviation that could be explained by measurement uncertainty or unusual local conditions. It is a structural violation of the pattern that decades of observation established. And it forces a question the Standard Model has no clean answer to. How does a black hole get that far ahead of its galaxy? The answer requires going back further than the first stars, further than the Dark Ages, further than the epoch of reionization. It requires going back to a time before any structure existed at all. And it requires taking seriously a theoretical framework that has been sitting in physics papers for over 50 years, waiting for exactly this kind of evidence. In 1971, Stephen Hawking and a colleague published a theoretical paper proposing that the chaotic, extremely high-density conditions of the very early universe could have allowed black holes to form directly, without any stars involved. The mechanism was straightforward in principle. The Big Bang was not perfectly uniform. Regions of slightly higher density existed from the first moments. In an environment that compressed and energetic, a region with enough excess density could collapse gravitationally before the outward pressure of the surrounding radiation had time to push back. The collapse would be near instantaneous on any meaningful timescale. A dense patch of primordial energy folding inward and becoming a black hole in the universe's first fraction of a second. Hawking called them primordial black holes. The theoretical framework predicted they could form across a wide range of masses, from tiny objects that would evaporate over cosmic time through the quantum process now named after him, to large ones that could persist through billions of years of cosmic evolution. He proposed that larger primordial black holes might serve as gravitational seeds, anchors around which gas would eventually gather and galaxies would eventually assemble. For 5 decades, this remained a compelling but unconfirmed idea. There was no obvious observational target to test it against. The prediction existed in the abstract, referenced in reviews, studied in detail by theorists, but floating without a confirmed physical example to give it weight. QS01 changes that situation. Every measurable property of QS01 is consistent with a black hole that predates the stars around it. The mass is too large to have grown in the standard way on the available timeline. The surrounding galaxy is too small and too chemically primitive to have hosted the stellar generations that normally feed black hole growth. The ratio of black hole mass to stellar mass is inverted in a way that only makes sense if the black hole came first, not grew slightly faster than the galaxy, not received an unusually good supply of infalling gas, but came first before the galaxy had any meaningful chance to build itself. Let us be precise about what too large to have grown in the standard way actually means numerically. Black holes cannot eat at an unlimited rate. When matter falls toward a black hole, it compresses and heats as it descends into the gravitational well, forming a disk of superheated plasma that spirals inward. That disk radiates. The outward radiation pressure from the infalling material creates a force opposing new material from continuing to fall in. At a specific accretion rate, the radiation pressure exactly balances gravity. The black hole cannot sustain faster eating without blowing away its own food supply. This ceiling is called the Eddington limit, and it is derived from the fundamental physics of radiation pressure. It is not a soft boundary, it is a confirmed physical constraint. At the Eddington rate, a black hole doubles its mass roughly every 25 to 30 million years. Starting from a seed of around 1,000 solar masses, which is already a large starting point for a stellar origin black hole, the math requires approximately 16 to 18 doublings to reach 50 million solar masses. At the Eddington rate continuously, that takes somewhere in the range of 400 to 500 million years of uninterrupted maximum rate accretion. The available window is 700 million years, minus the time required for the seed to form, minus the time required for enough gas to accumulate and begin the feeding process, minus any pauses or disruptions in the supply. Real black hole growth is not uninterrupted. Gas supplies get disturbed by galaxy dynamics. The black hole's own radiation periodically pushes material away. Mergers disrupt accretion flows. The realistic timeline is tighter than the theoretical maximum. Researchers who have run these numbers in detail describe the growth as sitting at the absolute boundary of what current physics allows, and in some scenarios beyond it. Either QS01 started with a much larger initial mass than stellar collapse produces, or it fed faster than the Eddington limit normally permits, or both. Neither option falls inside the standard model of black hole formation. A larger initial mass means something other than a dying star produced the seed. Direct collapse of a massive primordial gas cloud is one candidate, but it requires specific conditions including a radiation environment that suppresses the gas from fragmenting into individual stars before the whole cloud collapses. This is called the direct collapse black hole hypothesis. It is theoretically motivated, supported by some simulations, and has no confirmed observational example. A primordial origin requires no stellar collapse at all. The black hole forms from density fluctuations in the first second of existence, arrives in the dark ages seed with significant mass, and then grows through accretion during the hundreds of millions of years before the first stars ever ignite around it. By the time the universe has any visible structure, the black hole already has a substantial head start. This is the scenario that fits QS01 best. Not because the alternatives are ruled out, but because the combination of early age, inverted mass ratio, chemical signature, and suppressed star formation all independently point toward the same direction. A black hole that was already there before the galaxy began. The chemical signature deserves particular attention because it is often overlooked in favor of the mass numbers. QS01's surrounding gas and stars show extremely low abundance of heavy elements. In astronomy, anything heavier than helium on the periodic table qualifies as a metal. The oldest stars in the Milky Way have very low metal content because they formed early, before many generations of stars had died and scattered enriched material through the surrounding medium. The most metal-poor stars formed from nearly pristine gas. Their low metal content is a direct measurement of how early in cosmic history they assembled. QS01's system is not just metal-poor. It sits near the floor of what we would expect from a system with almost no prior stellar history. Spectroscopic analysis of the light from this system shows the absence of emission lines that would indicate chemically enriched gas. The fingerprint of multiple generations of stellar burning, dying and scattering is simply not there. This is enormously significant. If QS01's black hole had grown the conventional way, fed by gas cycling through dying stars, Those stars would have left their chemical mark on the surrounding medium. The gas would carry the signatures of oxygen produced in massive stars, carbon processed through stellar cores, iron forged in supernova explosions. None of that is visible in the data at the level it should be if conventional growth had driven this black hole to 50 million solar masses. The absence is the evidence. A black hole that formed before stellar nucleosynthesis had time to enrich the surrounding medium would look exactly like this. Clean, chemically primitive, sitting inside gas that has never been processed through the interior of a star. Scientists are careful to say this is consistent with a primordial or pre-stellar origin rather than confirmed. Consistency and confirmation are not the same thing. There are alternative explanations for low metal content. Heavy elements may have formed but been expelled from the system by the black hole's own energetic output before they could be detected. An unusually massive star could theoretically collapse directly without dispersing the enriched material it creates. These alternatives are explored in published work and cannot be dismissed. But the convergence of independent lines of evidence pointing in the same direction is striking. Age, mass ratio, chemical signature, suppressed star formation. Each piece of data, taken on its own, might have an alternative explanation. Together, they tell a consistent story about a black hole that did not grow inside a galaxy. They tell the story of a black hole that the galaxy grew around. That distinction, from product to anchor, is the structural reversal at the heart of everything that follows. And to understand its full implications, we need to spend some side the environment where it would have happened. The absolute darkness of the universe before stars. Picture a universe with no light sources of any kind, not a dim universe, not a faintly glowing universe. A completely dark one in the meaningful sense that no photons of visible light were being produced by any object anywhere. The Big Bang's initial glow had stretched beyond visible wavelengths during hundreds of millions of years of cosmic expansion. There were no stars yet, there were no galaxies, there was no fire. There was matter, organized into slow-drifting clouds and dark filaments of invisible scaffolding, and there was time passing in complete darkness. This is the cosmic dark ages. It lasted from roughly 380,000 years after the Big Bang, when the universe first became transparent, until somewhere between 100 and 200 million years in, when the first stars ignited. The exact boundary is still constrained by models and indirect observations rather than direct imaging. We have never seen the first star switch on. The signal is too faint, too redshifted, too embedded in foreground noise for current telescopes to resolve. What we know about the Dark Ages comes from physics, from what the universe must have been doing given its initial conditions and the laws of nature. Hydrogen and helium gas distributed unevenly according to the density fluctuations imprinted by inflation was slowly organizing under gravity. Dark matter halos deepened their gravitational wells. Ordinary gas fell into those wells along dark matter filaments, compressing toward the centers of the densest concentrations. This was the entire visible universe during the Dark Ages. Invisible structure growing in the dark, gas accumulating in the gravitational basins that dark matter provided, temperatures slowly dropping in the densest regions. No light, no chemistry beyond hydrogen and helium, no information traveling between different parts of the universe except through the relentless, patient pull of gravity. If a primordial black hole had formed in the first second of the Big Bang, it would have sat inside this darkness for hundreds of millions of years before any star appeared near it. During that time, it would not have been idle. Gas drifting into its gravitational reach would have fallen in, slowly adding to its mass. Dark matter passing through the region would have continued concentrating around it, deepening the well that would eventually attract the gas cloud that became QS01's galaxy. By the time the epoch of reionization began, by the time the first stars started ionizing the surrounding neutral hydrogen and flooding the universe with ultraviolet radiation, the black hole at the center of what would become QS01 may have already accumulated a substantial fraction of its eventual mass. It had hundreds of millions of years of quiet, dark feeding in an environment with no competitors, no feedback from nearby stars, and an essentially unlimited supply of pristine primordial gas. The first stars that formed near it would have found a gravitational anchor already in place. The galaxy, that assembled around it would have organized itself around a pre-existing center of mass rather than building from scratch. The entire formation history of this system runs in reverse compared to the standard model, where conventional theory says build the galaxy first, then grow the black hole inside it. QS01 suggests the opposite sequence was possible and perhaps common in the early universe. This matters beyond QS01 specifically because of what just it found while searching the broader deep field. QS01 was not the only unusual compact red object in the data. When the James Webb Space Telescope came online in 2022 and researchers began processing its deep field images, something kept showing up in the background of frames pointed at various regions of the early universe. Compact, faint, red-colored objects that did not match anything in existing catalogues. These were not artifacts or instrument glitches. They appeared repeatedly across independent observations in different areas of the sky, at consistent redshifts, placing them in the first billion years of cosmic history. Researchers started calling them little red dots. The name became the official informal designation used in published papers because it is accurate and because nothing more dignified seemed appropriate for objects that were simultaneously everywhere and completely unexplained. The confirmed facts about little red dots are limited but consistent. They are compact, meaning the light source is concentrated in a very small area of sky. They are found predominantly in the redshift range corresponding to 500 million to 1.5 billion years after the Big Bang. The red color comes from two distinct contributions: extreme cosmic redshift stretching the light's wavelengths toward longer values as the universe expands during transit, and local effects within or around the objects themselves pushing the color further toward red. The combination of high energy output in a tiny volume and the deep red color is what makes them distinctive, and also what makes them difficult to interpret. The scientific debate over little red dots split into two main positions. One side argued they were active galactic nuclei, meaning systems where a central black hole was consuming surrounding material at a high rate, and the released energy caused the surrounding gas and dust to glow across a broad range of wavelengths. The extreme compactness would reflect the small physical scale of the central energy source. The redness would reflect both redshift and dust in the local environment, absorbing and re-radiating shorter wavelength radiation as longer wavelength heat. The other side proposed they were extremely dense stellar clusters, galaxies where star formation had been so intense and so concentrated that the entire system shone brightly from a very small area. The redness in this scenario would come from the combined output of many massive stars filtered through local dust. No dominant black hole required. For most individual little red dots, the data available at the time could not cleanly distinguish between these interpretations. The spectral signatures were ambiguous. The resolution's insufficient to spatially separate what was happening at the center from what was happening in the surrounding region. QS01 resolved this ambiguity with unusual clarity. The spectroscopic data from QS01, boosted by the gravitational lensing magnification through Pandora's cluster, showed broad emission lines. Broad emission lines are a specific diagnostic. They arise when gas is moving at very high velocities around a compact massive object. The Doppler effect broadens the emission peak because some gas is moving toward the observer as it orbits, and some is moving away, smearing the emission into a wide profile. A dense stellar cluster does not produce this kind of broadening because stars in clusters do not orbit a central mass at the speeds required. Only a supermassive black hole creates the extreme gravitational well that forces surrounding gas to those velocities. The broad lines in QS01's spectrum confirmed a dominant central black hole, not implied it, not suggested it, confirmed it, through a measurement technique calibrated and validated across decades of black hole research. QS01 became the clearest confirmed example of a little red dot with a verified supermassive black hole at its center. The implication radiates outward to the rest of the little red dot population. If the clearest example has a confirmed massive black hole, and if the spectral properties that made QS01 identifiable as a black hole system are shared to varying degrees by hundreds of other little red dots, then a large fraction of those hundreds of objects likely also contain massive black holes. Not all of them, but enough to matter enormously for our picture of the early universe. Consider what a population of hundreds of massive black holes in the first billion years of cosmic history means for the standard formation model. Every one of them faces the same growth constraint that makes QS01 problematic. Every one of them sits in an environment where the surrounding galaxy is too young and too small to have produced the stellar generations that normal black hole growth depends on. Every one of them represents a data point inconsistent with the sequence the standard model predicts. One anomaly can be set aside as an outlier. A handful of anomalies can be attributed to unusual conditions. Hundreds of them, at consistent redshifts across independent observations from different parts of the sky, represent a systematic pattern. The standard model is not wrong about outliers. It may be wrong about the early universe as a whole. The deeper just looked, the more little red dots appeared, and with each new survey cycle the statistical case grew stronger that what the field had treated as rare exceptions were actually a common phase of early cosmic evolution. Massive black holes dominating their host systems before those systems had time to fully form. The galaxy second, the black hole first. And the question of mechanism, how these black holes reached significant mass before any galaxy could build around them, kept pointing back to processes that operated before stars existed. Primordial density fluctuations generating black holes in the universe's first moments. Dark matter halos undergoing their own internal collapse dynamics. Direct collapse of pristine gas clouds under conditions that the early universe provided and the modern universe does not. Let us spend time with the dark matter possibility because it is less widely discussed than primordial formation, but theoretically rich and directly relevant to what Jobst's observations are testing. Dark matter makes up roughly 27% of the total mass-energy content of the universe. Ordinary matter, everything that atoms are made of, accounts for only about 5%. The rest is dark energy, which governs the accelerating expansion of the universe. Dark matter is confirmed as a real component of the universe through multiple independent lines of evidence. Galaxy rotation curves move too fast to be explained by visible matter alone. Gravitational lensing of galaxy clusters bends light by more than the visible mass predicts. The large-scale structure of galaxy surveys matches simulations only when dark matter is included. What dark matter actually is at the particle level remains completely unknown. Decades of increasingly sensitive underground detectors, particle accelerator searches, and indirect astronomical searches have produced no confirmed direct detection. The candidates are numerous, weakly interacting massive particles, axions, sterile neutrinos, and others, none definitively identified. In the standard cosmological model, dark matter particles are assumed to be essentially collisionless. They interact through gravity, but pass through each other without scattering. This produces specific predictions for the internal structure of dark matter halos, particularly that the density should rise steeply toward the center in what is called a cusp. Observations of some dwarf galaxies and galaxy cluster cores suggest the central density profiles are flatter than standard cold dark matter predicts. This discrepancy has motivated a class of alternative models where dark matter particles can scatter off each other, transferring energy and momentum. In these self-interacting dark matter models, the internal dynamics of halos are different. Energy can be exchanged between particles in the halo interior. Under certain conditions, this heat transfer leads to a phenomenon called gravithermal collapse. The core region loses energy outward through particle scattering, contracts under gravity, increases in density, scatters more, loses more energy, contracts further in a runaway process that can accelerate dramatically once it passes a threshold density. The core collapses to extreme compactness. If that central dark matter density reaches a high enough threshold, a black hole can form directly from the dark matter itself. No ordinary matter involved. No gas, no stars, no stellar nucleosynthesis, just pure gravitational collapse of self-interacting dark matter in the halo's deepest region. A black hole formed this way would sit at the center of a dark matter halo whose internal structure had been restructured by the self-interaction phase. The surrounding environment would be primordial, dominated by pristine gas that had not yet been processed through stellar interiors. A galaxy would form afterward, organized by the gravity of the already present black hole. Stars would assemble from infalling gas slowly, and the resulting galaxy would be dominated in mass, by its central object for a potentially long period. This description maps onto QS01 with uncomfortable precision. The inverted mass ratio is expected if the black hole formed from dark matter collapse before the stellar population had time to build up. The chemical primitiveness of the surrounding gas is consistent because no stellar nucleosynthesis preceded the black hole's formation. The suppressed star formation could reflect the black hole's energetic output heating the surrounding medium before the galaxy stabilized. The compact nature of the entire system fits a scenario where structure organized around a pre-existing central mass rather than growing outward from diffuse gas clouds. The dark matter collapse model cannot be confirmed yet, and the reason is fundamental. Dark matter itself has not been directly detected at the particle level. We do not know if dark matter particles can self-interact at the rates required for gravithermal collapse. We do not know the mass of the dark matter particle, which constrains the scale of the structures that self-interaction would produce. Without knowing the particle properties, the model has adjustable parameters that can be tuned to match observations without actually constraining the physics. What the existence of QS01 does for this model is elevate it from an interesting theoretical speculation to a testable hypothesis. The object provides a target. Its properties constrain what a successful dark matter collapse model must produce. Future observations of QS01 and similar systems can be compared against predictions made by specific parameter choices within the model. Some choices will fail to match the data, others will survive. The survivors constrain the underlying particle physics of dark matter. This is how observational astronomy pushes back against theoretical physics, even when it cannot directly detect the particles involved. The universe runs experiments that laboratory equipment cannot replicate, at energies and densities unavailable on Earth, over timescales longer than human history. Just is reading the results of those experiments from the light they left behind 13 billion years ago. The 29 hours dedicated observation that went into the most detailed spectroscopic analysis of QS01 revealed an additional layer of complexity that neither the primordial black hole nor the dark matter collapse model had specifically predicted, but that both can accommodate. The ultraviolet emission from QS01's hydrogen gas, specifically the Lyman alpha emission produced when ionized hydrogen recombines and electrons drop to their ground state, came back with a distorted profile. The shape of the emission peak was asymmetric. One side of the profile showed less of the expected redshift than models predicted. The line was broader and less symmetric than the signal from a clean, unobstructed source would produce. The research team's interpretation pointed to dense clumps of neutral hydrogen gas surrounding the black hole system, scattered unevenly through the region rather than distributed smoothly. Neutral hydrogen is extremely effective at absorbing Lyman alpha photons. A photon traveling outward from the central source hits a cloud of neutral gas, gets absorbed, then remitted in a random direction. The process can repeat many times before the photon finally escapes the system. The result is a light path that scatters and bounces rather than traveling cleanly outward, and the spectral signature of that scattering is exactly the asymmetric, broadened emission profile that the 29-hour observation recorded. This is classified as the team's leading interpretation, rather than a confirmed conclusion, because distinguishing between different gas distribution models at this redshift and this angular resolution remains technically demanding. But it is a physically grounded interpretation based on well-understood radiative transfer physics. The existence of clumpy neutral hydrogen around QS01 at this stage of cosmic history is itself informative. In a system that had proceeded through many generations of star formation and stellar feedback, the surrounding gas would have been processed and redistributed in ways that tend toward greater uniformity over time. Clumpy, irregular neutral gas is more consistent with pristine material that has not been through extensive stellar cycling. The clumps may represent inflows from the intergalactic medium, streams of primordial hydrogen falling into the system's gravitational well, or they may reflect turbulence created by the black hole's own energy injection before the surrounding medium had settled into a more organized distribution. Either way, the clumpy gas structure adds to the picture of a system in an extremely early chaotic state. Not a mature galaxy with a massive black hole at its center. not even a young galaxy in the process of settling, something rawer and more primitive, a gravitational concentration of material that has barely begun to organize itself around the dominant object at its center. There is also the question of why QS01 appears so faint, despite containing a 50 million solar mass black hole that should by all rights be blazing. Active black holes feeding on surrounding material produce some of the most luminous objects in the observable universe. Quasars, powered by supermassive black holes consuming gas at near Eddington rates, can outshine entire galaxies containing hundreds of billions of stars. QS01, by contrast, appears as a barely visible red speck even with the lensing magnification that made spectroscopic analysis possible. The answer is the same clumpy neutral hydrogen that distorted the Lyman alpha profile, combined with dust. Astronomical dust, consisting of tiny grains of silicates and carbon compounds produced by dying stars and distributed through the surrounding medium, absorbs shorter wavelength radiation and re-radiates it as infrared heat. The combination of neutral hydrogens scattering ultraviolet photons and dust-absorbing and thermally re-radiating additional radiation across a broad wavelength range acts as a double filter over the entire system. What reaches the telescope is a reduced, reddened, distorted version of the total energy output. The actual luminosity of the black hole is larger, possibly much larger, than the observed brightness indicates. This dimming effect carries a broader implication for the little red dot population. If QS01 is this heavily obscured and still detectable at this redshift, other little red dots with similar or heavier obscuration may be invisible even to JOUST. The number of massive black holes in the early universe may be substantially larger than current counts suggest. The early cosmos may have been far more energetically active than any telescope has yet revealed, with dozens or hundreds of heavily shrouded black holes radiating intensely behind curtains of primordial gas and dust, contributing energy to the surrounding intergalactic medium and accelerating the reionization process in ways the current models do not account for. This systematic undercount, if confirmed, would require revisions not just to galaxy formation models, but to the entire accounting of how the epoch of reionization proceeded and how quickly the neutral hydrogen fog between the first galaxies burned away. The rate and character of reionization depends on knowing the total radiation budget from all available sources. If a significant fraction of those sources are hidden behind obscuring material, the budget is wrong and everything downstream of it in the model needs adjustment. The scale of the problem that QS01 represents is not limited to one object or even to the little red dot population. It reaches into the fundamental history of how structure formed in the universe, how the sequence of events that ultimately produced planets, chemistry, and living organisms got started, and whether the standard model of cosmology has been systematically missing a key ingredient from the very beginning. Let us put numbers to the timescale problem one more time, because the difficulty compounds in ways that a casual statement of the mass does not fully convey. The universe began 13.8 billion years ago. QS01's light left its source 13.0 billion years ago, when the universe was 700 million years old. That means the entire observable history of the object we are discussing, from the first moment it could have begun forming after the Big Bang to the moment its light left and began traveling toward us, spans 700 million years. Within that window, a black hole reached 50 million solar masses. The Sun has a mass of 2 × 10 to the power of 30 kilograms. 50 million of those suns is a mass so large that spelling it out in kilograms requires a number with no meaningful intuition attached to it. The more relevant comparison is this. Our own galaxy's central black hole, Sagittarius A star, weighs 4 million solar masses. It grew to that mass over 13 billion years, starting from stellar collapse seeds, growing through accretion, fed by the full resources of the Milky Way. QS01's black hole achieved more than 12 times that mass in 1/19 the time, in a system tiny enough that the entire thing spans about 2% of the Milky Way's diameter. The Eddington limited growth calculation shows that even under maximally favourable conditions, reaching 50 million solar masses in 700 million years from a stellar origin seed is at the boundary of what the known physics allows and likely beyond it when realistic interruptions to accretion are considered. starting from a significantly more massive seed relaxes the problem considerably. A primordial black hole that formed in the first second of the universe with thousands or even millions of solar masses in place would need far fewer doublings to reach 50 million, and would have had more time, including the long dark centuries before any stars existed, to add mass through accretion of the surrounding primordial gas. This is not a marginal adjustment to the model. It is a different starting state, a different chapter 1, a different answer to the question of what the universe was doing before the first light. And if that different chapter 1 is correct, if the universe seeded massive black holes in its very first moments, then the history we have been teaching for decades is missing its actual beginning. The story of cosmic structure does not start with gas clouds and stars and slowly growing black holes. It starts with black holes already present, waiting in the dark, organizing the gas that would eventually produce stars, seeding the galaxies that would eventually host chemistry, eventually producing the conditions for the kinds of complexity that sit here now, billions of years later, watching the light from that original darkness reach a telescope and slowly give up its secrets. The gravitational lensing that made all of this measurable deserves its own moment of appreciation, because without it, none of the spectroscopic confirmation that QS01's story requires would have been possible. Einstein's general theory of relativity, published in 1915 and confirmed observationally in 1919 through measurements of starlight bending around the sun during a solar eclipse, established that mass curves the geometry of space. Light, traveling through curved space, does not travel in a straight line in the conventional sense. It follows the geometry of the space it passes through. Near a massive object, the available paths for light curve toward that object. Light from a distant source passing close to a massive foreground object arrives at the observer from a slightly different, apparent direction than it would without the intervening mass, and it arrives brighter because as the curvature focuses light from a wider area of the source toward the observer. When the foreground mass is large enough and the alignment is close enough, the lensing effect is dramatic. Sources behind galaxy clusters can appear as arcs, rings, or multiple distinct images depending on the precise geometry. The magnification can reach factors of 10, 20, or more, bringing sources into detectable range that would otherwise fall below the sensitivity threshold of the best available telescopes. Pandora's cluster provided this service for QS01 with unusual effectiveness. The alignment between the cluster and QS01 produced 3 separate images of the source, each representing light that took a different path around the cluster and arrived from a slightly different apparent direction. Scientists confirmed all 3 as the same source by matching their spectral signatures, then used the 3 independent data streams to cross-check measurements and probe the foreground cluster's own structure. The magnification delivered the crucial resource: photon count high enough to perform high-resolution spectroscopy on a source that would otherwise have been unresolvable. Spectroscopy at this level of detail, spread across the full range of relevant wavelengths, and with sufficient signal-to-noise to identify broad emission lines, measure their widths accurately, and map the distorted Lyman alpha profile, was only possible because nature provided an amplifier no human technology could have replicated. This is not a trivial point in the context of what this discovery means for the future of the field. The current confirmed understanding of QS01 exists specifically because one object happened to sit behind one of the most powerful natural gravitational lenses known, and astronomers happened to be conducting a survey of that lens. Remove the fortuitous alignment and QS01 is one of hundreds of little red dots with insufficient signal for detailed characterization. It remains in the population of unexplained objects rather than becoming the best characterized example of a new class. How many QS01 equivalent systems exist outside favorable lensing geometries, too faint for detailed spectroscopic analysis with current instruments, contributing to the head count of little red dots, but denying us the detailed measurements that would confirm or constrain their nature? The answer is almost certainly many. The little red dot population as currently observed is almost certainly an undercounted, undercharacterized sample. GWAST is finding them everywhere it looks deeply. The fraction with strong lensing magnification is small. The fraction with the specific Pandora's cluster level of amplification is very small. What QSO-1 reveals about the class is likely representative of a much larger population that current technology cannot study at the same level of detail. The next generation of instruments addresses this directly. The extremely large telescope currently under construction on Cerro Amazonas in Chile's Atacama Desert will deploy a primary mirror 39 meters in diameter, collecting roughly 36 times more light per unit time than JWST's 6.5-meter mirror. The increase in light-gathering power translates directly into better signal-to-noise on faint sources, finer spectral resolution, and the ability to study objects at similar distances to QSO-1 without needing extreme lensing magnification. Individual little red dots that are currently statistical entries in a catalogue will become spectroscopically characterizable targets. The Nancy Grace Roman Space Telescope, a wide-field infrared survey mission, will cover large areas of the sky at sensitivity above current capabilities, identifying many more little red dot candidates across a range of redshifts. Building the statistical sample that distinguishes between formation models requires numbers. One object can inspire a theory, hundreds of objects can test it, thousands can confirm or rule it out. Roman will build toward those numbers. Gravitational wave observatories add a completely independent measurement channel. If primordial black holes formed across a range of masses in the early universe, some of them merged with each other in the billions of years that followed. Those mergers produced gravitational waves. The Laser Interferometer Space Antenna, a planned space-based detector with arm lengths of millions of kilometers, will be sensitive to gravitational wave signals from merging black holes in the mass range relevant to primordial formation scenarios. A detection of early universe black hole merger signals, independently of any electromagnetic observation, would provide strong additional evidence that a population of massive black holes existed in the primordial universe. The scientific case for QSO-1's primordial or pre-stellar origin will ultimately be assembled from multiple independent lines of evidence, each using different physics and different instruments to probe the same underlying reality. The convergence of electromagnetic observations, gravitational wave detections, and theoretical modeling from simulations of the early universe will determine whether the primordial black hole explanation survives full scientific scrutiny. That process takes time. It takes multiple independent teams examining the same data from different angles. It takes alternative explanations being tested and either surviving or failing. It takes new observations that the competing models make different predictions about, measurements that can distinguish between them. This is the scientific method as it actually operates at the frontier, and it does not deliver clean answers on demand. It delivers narrowing uncertainty over years and decades. What the current state of the evidence justifies saying is this: the discovery of QSO-1 is real. The black hole mass measurement is confirmed through established methodology. The inverted mass ratio relative to the host galaxy is confirmed. The extreme early epoch of the object is confirmed through redshift measurement. The chemical primitive nature of the surrounding medium is consistent with the spectroscopic data. The broad emission line confirmation of a dominant central black hole is established. The clumpy neutral hydrogen structure detected in 29 hours of dedicated observation is the team's published interpretation of real spectral data, currently awaiting independent confirmation through additional observation. The implications of those confirmed facts for standard galaxy formation theory are serious and cannot be resolved within the existing framework without major modifications. The object demands an explanation that existing models do not cleanly supply. The primordial black hole scenario, proposed theoretically more than 50 years before this discovery, fits every confirmed property of QSO-1. It requires no fine-tuning, no unusual conditions specific to this one system. If it is the correct explanation, it was predictable in principle from physics that predated the birth of most people alive today. Hawking published his theoretical framework for primordial black holes in 1971. He spent decades developing the associated physics, including the quantum evaporation process that now carries his name. He died in 2018, 4 years before JWST launched and 7 years before the team published the 29-hour spectroscopic analysis of QSO-1. He never saw the telescope that may have found the first observational confirmation of the objects he spent a career predicting. The object he described, born in the chaos of the universe's first second from primordial density fluctuations, carrying no chemical history of stellar nucleosynthesis, sitting at the center of a galaxy it effectively predates, surrounded by pristine hydrogen that has never been processed through a star, matches what the most powerful telescope humanity has ever built, found behind and a gravitational lens 13 billion light-years away. That alignment between 50 years of theoretical prediction and a single pixel of data from deep space is not confirmation. It is the beginning of a conversation between theory and observation that has never previously been possible. The universe spent 13 billion years carrying this evidence across the cosmos. We spent 50 years building the tools to read it. The reading is not finished. But what has been read already is enough to take seriously a revision to the most fundamental story in all of cosmology, the story of what came first. If the universe built its most massive objects in its first second, before chemistry, before light, before any of the processes that we associate with cosmic evolution, then the history we describe when we describe the origins of everything is missing its true opening chapter. The stars came second, the galaxies came third. The chemistry that produced every atom in every living thing came somewhere further down the sequence. First came the darkness. And inside the darkness, already dense and already dominant, already bending the space and time around it, already organizing the raw material that would eventually become everything we know, a black hole. The universe did not start with light. It started with gravity. And gravity, given enough mass concentrated in enough space, always wins. When we look at Pandora's cluster through Jostie's mirrors, we are looking at something that exists in a hierarchy of scales almost impossible to hold in mind simultaneously. The mirrors collect photons that left their source before our sun existed. Those photons carry information about an object smaller in extent than 2% of the Milky Way, containing a gravitational object that shaped the structure of an entire galaxy system across billions of years of subsequent evolution. The information is encoded in wavelengths stretched by cosmic expansion, distorted by clumpy neutral gas, filtered through dust, split by a gravitational lens into 3 copies, and finally converted by the telescope's detectors into numbers that human beings analyze in offices and universities and collaborations spread across continents. Every photon that reached those mirrors is an emissary from the universe's childhood, sent before our entire solar system existed. The fact that they arrived in precisely the right configuration to be readable is not something we arranged. It is something the universe arranged through the alignment of Pandora's cluster, through the specific density fluctuations that placed QS01 behind it, through the geometry of cosmic expansion over 13 billion years. We did not find QS01. QS01 found us, with a message written in stretched light and chemical silence that took 50 years of theoretical work to understand how to read. The message in its simplest form is this: you are looking at the beginning of everything, not the beginning of the observable universe from the cosmic microwave background, not the beginning of structure from the first stars, the actual beginning of the gravitational skeleton that organized everything that came after, the moment when the universe decided, in a fraction of a second of chaotic extreme density, to plant the seeds of every galaxy that would ever form. One of those seeds became QS01. Another one possibly became the center of the Milky Way. Another one might have become the anchor around which the galaxy containing the solar system organized itself 4.5 billion years ago. The iron in your blood was forged in stars. Those stars formed inside galaxies. Those galaxies organized around gravitational anchors that may be as old as time itself. You are, in the most literal physical sense, the product of a process that started before anything we can directly observe. The universe wrote its first sentence in the dark, in a language of pure gravity, and everything that followed, every star, every world, every molecule capable of examining its own origin, is a later paragraph in a document that began in the first second of existence. The little red dot behind Pandora's cluster may be the oldest word in that document, and we are only just beginning to read it. There is a question that gets asked less often than it should in discussions about black holes, this massive and this ancient, and that question is, what is it actually like inside that system? Not in the speculative sense of asking what falls into a black hole and survives, which is a thought experiment with no observational traction, but in the physical sense of asking what the conditions are in the space around QS01's black hole, in the gas and sparse stellar material that surrounds it, in the environment where whatever processes are still ongoing right now, more than 13 billion years after the light we measured left the scene. The first thing to establish is that we have no idea what QS01 looks like today. The light we analysed left that system when the universe was 700 million years old. It then spent 13 billion years crossing the expanding universe before arriving at the telescope. In those 13 billion years, QS01 has had the same span of time that separates us from the Big Bang itself to continue evolving. The black hole may have grown dramatically. It may have merged with other black holes during a galaxy collision. The surrounding galaxy may have built up hundreds of billions of stars. The system may look almost unrecognizable compared to what we measured. We will not know what it looks like now for another 13 billion years, when the light currently leaving it reaches us. This is the consistent, strange reality of observational cosmology. Every measurement we make of a distant object is a historical document. Every telescope is an archive. The farther the object, the older the record. Just looking at QS01 is equivalent to finding a photograph taken 13 billion years ago and examining it for physical evidence. The subject of the photograph has aged by the entire history of the universe since the shutter clicked. What we can reconstruct from the measurements is what conditions were like at the moment of observation. And those conditions were extraordinary even by the standards of the extreme early universe. 50 million solar masses concentrated inside a black hole creates a gravitational field at the event horizon that defies ordinary intuition. The event horizon itself, the boundary where escape velocity exceeds the speed of light, spans a physical diameter of approximately 300 million kilometers for a black hole of this mass. For reference, that is roughly twice the distance from the Earth to the Sun. The entire region within which gravity is so strong that light cannot escape spans a physical scale larger than the orbit of Venus around our Sun. Crossing that boundary does not feel dramatic from the inside for a massive black hole of this size. The tidal gradient at the horizon, the rate at which gravity changes over a short distance, is actually gentler for larger black holes. An object approaching the event horizon of a 50 million solar mass black hole would cross the boundary before being meaningfully stretched by tidal forces. The transition from outside to inside is physically smooth, at least in terms of what an infalling observer would experience locally. The drama is in the math, in what the crossing means for any future trajectory, not in any detectable local signal at the moment of entry. Outside the event horizon, however, in the active feeding region of the accretion disk, conditions are anything but gentle. Gas spiraling inward under gravity compresses as it descends, heating through friction and magnetic turbulence to temperatures of millions of degrees in the innermost orbits. This plasma glows across the full electromagnetic spectrum, from radio waves through visible light to X-rays and beyond. The radiation pressure from this superheated disk is what creates the Eddington limit, the ceiling on how fast the black hole can accumulate mass before the outward radiation pushes new material away. Perpendicular to the disk, along the rotation axis of the black hole, the physics can organize into something even more dramatic. When the conditions in the inner accretion region are right, the strong magnetic fields threading through the plasma can funnel material and energy into tight jets, columns of superheated plasma moving at a significant fraction of the speed of light, projected outward from both poles of the black hole's spin axis. These jets can extend for thousands of light years into the surrounding galaxy, injecting enormous amounts of energy into the surrounding gas far from the central object. Jet-driven feedback is confirmed in nearby galaxies where we can resolve the spatial structure and directly observe the jets interacting with the surrounding medium. In some cases, jets from central black holes have carved enormous cavities in the hot gas that fills galaxy clusters, pushing material away from the center over tens of millions of years. The energy involved dwarfs anything stellar populations produce and can effectively regulate the entire thermal state of gas across scales much larger than the galaxy itself. In QS01, at 700 million years after the Big Bang, whether jets were active at the moment of observation is not directly established by the current data. The 29-hour spectroscopic campaign revealed the gas structure through Lyman alpha emission. But jet activity leaves different signatures that would require additional observations at different wavelengths to confirm or rule out. What the data does show is that something energetic was shaping the surrounding gas, heating or displacing material in ways consistent with the black hole's output, suppressing star formation in the surrounding galaxy. Whether that energy came through disk radiation, through jets, or through some combination remains an open observational question. The suppressed star formation itself is one of the most consequential aspects of QS01 for understanding how the first galaxies evolved. Star formation in the modern universe proceeds through a multi-step process. Molecular clouds of gas and dust cool and condense. Density irregularities within those clouds grow under gravity. Clumps dense enough for nuclear fusion form and ignite. In the early universe, before heavy elements were available as cooling agents, this process was harder. Gas had to reach higher densities and temperatures before stars could form, which is why the first stars were massive. But in QS01, even the limited star formation that one might expect given the available gas and the conditions of the epoch of reionization seems to have been further suppressed. The stellar mass of the surrounding galaxy is far lower than models predict for a dark matter halo of this mass at this redshift. Something kept the gas from efficiently converting into stars. The black hole as its own suppressor is the leading explanation. As QS01's black hole fed, it released energy. That energy heated the surrounding gas. Heated gas cannot cool efficiently enough to collapse into stars. The same engine that was growing the black hole was simultaneously preventing the galaxy from growing the stellar population that would normally dominate the mass budget. The faster the black hole grew, the more energy it injected and the less opportunity the surrounding galaxy had to build itself up. This feedback loop, operating at the earliest stage of galaxy formation before the galaxy had a meaningful chance to establish itself, is qualitatively different from feedback in mature galaxies. In a mature galaxy, black hole feedback quenches star formation that is already proceeding, transitioning an actively star-forming young galaxy into a passively evolving one. In QS01, the feedback may have operated from the very beginning, not quenching an established system but preventing one from ever fully forming. The galaxy did not die, it was stunted before it could grow. The result is what we observe: a gravitationally dominant black hole surrounded by a thin, barely assembled collection of gas, and a stellar population too small to come close to matching the central mass. This raises a broader question about the relationship between the very first black holes and the very first galaxies. If primordial black holes seeded the gravitational wells that organized early structure, and if the energy output of those black holes simultaneously regulated how much stellar mass could assemble around them, then the black holes were not passive beneficiaries of galaxy formation. They were active architects, determining from the outset how much galaxy could form around them, how quickly, and with what chemical composition. The M-sigma relation, the tight empirical relationship between central black hole mass and host galaxy properties observed across hundreds of mature galaxies, might then be understood differently than it has been. Rather than reflecting a fundamental coevolution where both components grew together and influenced each other symmetrically, it might reflect the end state of an asymmetric process. The black hole, which arrived first, determined the ceiling on the galaxy's growth through feedback. The galaxy, growing within that ceiling over billions of years, reached a mass proportional to the black holes because the black holes set the limit. The ratio we observe in mature systems is not evidence of simultaneous coevolution. It is evidence that the black hole always won, and what we call the M-sigma relations is simply the average of how much the galaxy was allowed to grow before the black hole's feedback finally constrained it to a fixed fraction of its own mass. QS01 shows us what the system looked like before the equilibrium was reached, before the galaxy had time to catch up to the limit the black hole set. A snapshot of the early universe that preserves the asymmetry before billions of years of subsequent evolution erased it. The cosmic web that organizes every galaxy visible in deep field surveys today is the macroscopic expression of density fluctuations that existed in the Big Bang's earliest moments. The filaments and voids that map out where galaxies cluster and where space is almost empty trace the amplification of those initial density differences over 13 billion years of gravitational evolution. Where density was slightly higher, gravity accumulated more material, which increased density further, which attracted still more material in a self-reinforcing cascade. Where density was slightly lower, material drifted away toward the denser neighboring regions, and those voids grew emptier over time. The specific pattern of the cosmic web, its particular arrangement of filaments and nodes and sheets, reflects the particular spectrum of density fluctuations imprinted by the inflationary period, the brief epoch of extremely rapid expansion that cosmologists believe occurred in the first tiny fraction of a second after the Big Bang. Inflation stretched quantum fluctuations from the subatomic scale to cosmic scales, imprinting a specific pattern of density variations across what would become the observable universe. The exact shape of that pattern, its statistical properties, and the amplitude of fluctuations at different scales is one of the things the cosmic microwave background encodes, and measuring it has been one of the major scientific programs of the past several decades. If primordial black holes formed from the largest density fluctuations in the early universe, their distribution across space would not be random in the simple sense. They would preferentially form in regions where the density fluctuations were above a critical threshold. Those regions would also be, by definition, the same regions where dark matter would eventually form the densest concentrations and around which the largest galaxy clusters would eventually assemble. Primordial black holes and the most massive structures in the modern universe would share a common ancestor in the same high-density regions of the early cosmos. The implication is that looking at the large-scale structure of the universe today, the arrangement of galaxy clusters and supervoids across hundreds of millions of light-years might carry the fingerprint of where primordial black holes formed 13 billion years ago. The positions of the most massive clusters today, the locations of the richest environments in the cosmic web, might trace the original sites of primordial black hole formation from the universe's first second. Reading that fingerprint would require comparing the observed structure of the universe with predictions from models of primordial black hole formation at different mass scales and different formation thresholds. The comparison would either match or fail to match, and the result would constrain not just whether primordial black holes formed, but the details of the inflationary physics that produced the density fluctuations they formed from. This is a scientific program of enormous scope, and QS01 is one of the observational anchors that makes it concrete rather than purely theoretical. Without a confirmed example of an early massive black hole consistent with primordial formation, the program is building models without a target. With QS01 and the broader little red dot population as targets, the models have real constraints to match. One of the persistent difficulties in discussing primordial black holes as dark matter candidates, which is separate but related application of the same theoretical framework, is that the mass range where primordial black holes could account for a meaningful fraction of dark matter is severely constrained by observations. Very light primordial black holes would have evaporated through Hawking radiation over the age of the universe. Black holes in the mass range of asteroids to small moons are constrained by microlensing surveys that would have detected them if they were sufficiently abundant. Black holes in the stellar mass range face constraints from gravitational wave merger rates measured by LIGO and Virgo. Black holes in the mass range of millions to billions of solar masses, the kind that QS01 represents, face constraints from their effect on the structure of galaxies and galaxy clusters. None of these constraints rule out primordial black holes entirely. They constrain what fraction of dark matter could be in primordial black holes at different mass scales. Some mass ranges allow primordial black holes to account for a small but non-negligible fraction of dark matter. The primordial black holes suggested by QS01 are not primarily being discussed as dark matter candidates because their mass is too large for them to be abundant enough to contribute significantly to the dark matter budget without producing observable effects that are not seen. Instead, they are being discussed as seeds for galaxy formation, and in that role, their mass is appropriate. The distinction matters because it affects how the primordial black hole scenario connects to the broader problem of dark matter's identity. Finding that some black holes formed primordially does not solve the dark matter problem. Dark matter is required in enormous quantities, distributed in specific ways, behaving consistently with being collisionless and pressureless. The contribution from primordial black holes in the QSO1 mass range is too small and too clustered to account for the full dark matter component. What primordial black holes would do for dark matter models is add a confirmed population of primordially formed objects, demonstrating that the density fluctuation regions from inflation were large enough in some regions to produce black holes, and providing a data point that constrains inflation models independently of the cosmic microwave background measurements. The inflationary period remains one of the most theoretically rich and observationally challenging areas of modern cosmology. The standard picture of inflation, a brief epoch of exponential expansion driven by the energy of a hypothetical field called the inflaton, produces a nearly scale-invariant spectrum of density fluctuations that matches the cosmic microwave background observations remarkably well. But the nearly in scale invariant is important. On small scales, some inflation models predict an enhancement of the density fluctuation amplitude, a departure from the fairly flat spectrum that would produce more large density regions and more potential sites for primordial black hole formation. These enhanced small-scale fluctuation models have been studied for decades as one of the mechanisms for producing primordial black holes in meaningful abundance. Measuring the actual primordial black hole mass distribution from objects like QSO1 would test these models directly. If QSO1 mass primordial black holes exist in the observed abundance across the little red dot population, and if similar objects continue to be found in larger numbers as JDST accumulates data, the implied primordial black hole formation rate constrains the enhancement in the small-scale power spectrum that inflation would have had to produce. Some inflationary models would survive those constraints, others would not. This is the kind of connection between cosmological observations and fundamental physics that makes a discovery like QSO1 significant far beyond its immediate domain. A tiny red pixel in a JST image is not just a data point at about one unusual galaxy. It is a measurement that reaches back through the entire history of the universe to the physics of the first fraction of a second, constraining the energy scale and field dynamics of the period that set the initial conditions for everything that followed. The scope of what we can learn from this one object, extended through a program of follow-up observations and theoretical modeling, is genuinely extraordinary, and the fact that it was found almost incidentally while the telescope was conducting a broad deep field survey, rather than hunting specifically for primordial black hole evidence, suggests that the universe is not being stingy with this information. It is there in the data. The challenge is building instruments sensitive enough to read it and theoretical frameworks sophisticated enough to interpret it. Let us return briefly to the claim that the surrounding galaxy's chemical signature, the near absence of heavy elements, is one of the strongest pieces of evidence for a black hole that predates stellar activity. The claim is worth unpacking in more depth because the spectroscopic evidence for it is subtle, and the interpretation requires understanding what astronomers mean when they say the absence is the signal. When a star more massive than about 8 times the mass of the Sun reaches the end of its main sequence life, the core that has been fusing progressively heavier elements collapses in a fraction of a second, while the outer layers explode outward in a supernova. The explosion is so energetic that it forges additional heavy elements through rapid neutron capture processes, the R process, which builds the heaviest elements in the periodic table up through uranium and beyond. The ejected material then mixes with the surrounding interstellar medium. The next generation of stars that forms from that enriched medium contains more heavy elements than its predecessors. Each cycle of star formation, stellar evolution, and supernova enrichment adds to the chemical complexity of the galaxy's gas reservoir. This enrichment history is readable in stellar spectra. Metal lines, absorption features from heavier elements in stellar atmospheres, grow more prominent with each generation of enrichment. The oldest stars in the Milky Way halo have metal abundances thousands of times lower than the Sun, reflecting their formation from gas that had not yet been through many enrichment cycles. The Sun's relatively high metal content reflects its status as a third or fourth generation star, incorporating material from multiple prior stellar generations worth of nucleosynthesis. In QS01, the absence of strong metal emission and absorption signatures in the spectral data from both the stars and the surrounding gas indicates that the system had not been through extensive enrichment cycles at the time of observation. The lack of iron lines, the weakness of oxygen and carbon signatures, the overall chemical primitiveness of the spectrum all point to a system that was in its first or perhaps second stellar generation at most, with most of its gas still bearing the pristine composition of the primordial universe. This is consistent with QS01 having formed very recently, in cosmic terms, before the observation epoch, but it is also consistent with something more specific, the black hole itself having formed before any stars existed, meaning that the gas around it had never been cycled through stellar interiors before. A black hole that predates the first stars in its region would be surrounded by gas carrying the composition of the pre-stellar universe. As the first stars formed around it during the epoch of reionization, and some of them began to die and enrich the surrounding medium, the process of chemical evolution would have been just beginning at the moment QS01's light left its source. The chemical evidence alone cannot distinguish between a system that is simply very young and a system whose central black hole predates any stellar activity. But combined with the mass ratio, the age, and the growth rate considerations, it adds a consistent piece to a picture that is coherent only if the black hole has a pre-stellar origin. Science does not move through revelation, it moves through accumulation. Each measurement adds a constraint. Each failed alternative narrows the space of viable explanations. Each successful prediction from a theoretical model strengthens the case that the model captures something real. The case for QS01 being the first observational evidence for a primordial black hole is currently at the stage of consistent accumulation. Nothing has broken it, nothing has confirmed it definitively. The process continues. What drives that process forward, what will ultimately resolve the debate one way or another, is more data from more objects at more wavelengths, analysed by more independent teams using more sophisticated theoretical models. The scientific community is pursuing all of these fronts simultaneously. New spectroscopic campaigns as on QS01 itself are planned or in progress. Statistical analyses of the full little red dot population are ongoing. Theoretical models are being refined to make more specific predictions that distinguish between formation scenarios. Gravitational wave observatory data is being scanned for signals consistent with early universe black hole mergers. The width of the uncertainty is narrowing, and it will continue to narrow with every new observation. What we know for certain right now is that the universe contains an object that should not exist according to the rules we thought we understood. A 50 million solar mass black hole at the edge of the observable universe, sitting inside a galaxy so underdeveloped that the galaxy itself weighs less than half the black hole. The light from this object left before our planet existed. It travelled through an expanding universe, bent around a gravitational lens split into 3 copies, and arrived at a mirror the size of a tennis court floating in space 1.5 million kilometers from Earth, where detectors converted it into numbers that human beings spent months analysing. Those numbers do not fit the model. They require the model to be wrong in a specific way, and the specific way the model needs to be wrong points toward a mechanism that has been theoretically described since 1971 and has been waiting for this kind of evidence ever since. Whether or not the primordial explanation holds up through the full process of independent verification and peer review, the discovery of QS01 has already changed the conversation. It has elevated theoretical proposals that were previously untestable to the status of testable hypotheses. It has provided a specific observational target against which competing models can be checked. It has given the scientific community a reason to look more carefully at the little red dot population with the explicit question of whether massive pre-stellar black holes were common in the early universe rather than exceptional. And it has introduced into the mainstream scientific literature the serious possibility that the universe's first significant structures were not stars or gas clouds but black holes forming in darkness before anything else had a chance to begin. There is something in that possibility that is difficult to fully absorb. We grow up with a mental image of the cosmos as fundamentally luminous, filled with light from stars in every direction. The night sky is dark only because of geometry and the finite age of the universe, not because the cosmos lacks light sources. Light is what we use to observe everything. Light is what we receive from the past. Light is what defines our access to any information about distant objects. Our entire relationship with the universe beyond Earth is mediated by electromagnetic radiation, and the stars that produce that radiation feel like the foundational feature of the cosmos. But the universe spent a significant portion of its early history in darkness. Not metaphorical darkness, not the kind of darkness you find in a room with the lights off, where infrared radiation from bodies and objects still provides a technically detectable signal. Actual, comprehensive electromagnetic darkness, no visible photons being produced by any source anywhere. And if the primordial black hole hypothesis is correct, the most important structural objects in the universe were formed and operating during that darkness, invisible to any electromagnetic telescope, building the gravitational architecture that light-emitting objects would eventually fill. The universe's real foundation is not light. It was never light, it was gravity. And the most intense concentrations of gravity that the universe produced began forming before any photon was set free to tell us about them. We are, in a literal sense, descendants of a process that operated entirely in the dark. The first chapter of cosmic history was written without witnesses, in a language we are only now, 13 billion years later, developing the instruments and theories to read. QS01 is not just an unusual galaxy. It is a message from that unwitnessed beginning, the smallest looking thing in the image, the oldest story in existence, and we are only partway through the first reading. The question of whether our own galaxy's central black hole, Sagittarius A star, has a primordial origin is one that the existence of QS01 forces onto the table in a way it was not previously sitting. Before QS01, the question was purely theoretical. There was no observational target to anchor it. Now there is, and the comparison is uncomfortable in a specific way. Sagittarius A star weighs 4 million solar masses. It sits at the center of a galaxy containing between 200 and 400 billion solar masses of stars, along with enormous additional amounts of gas, dark matter, and other material. It is, by every measure of the M-sigma relation, a well-behaved central black hole. Its mass is proportionate to the galaxy around it. It fits the established relationship exactly as expected for a galaxy of the Milky Way's size and type. Nothing about it taken in isolation demands an unusual explanation, but QS01 asks a different question about Sagittarius A star. Not whether it fits the mature relationship, which it does, but where it came from before that relationship was established. At 700 million years after the Big Bang, when QS01's light left its source, what did the precursor to the Milky Way look like? Was there already a black hole at its center, and if so, how did it form? The oldest stars in the Milky Way, found primarily in globular clusters, and the galactic halo have ages approaching 13 billion years. They formed very early in the galaxy's history, from gas that was already being organized by whatever gravitational structure existed at the time. Reading the chemical signatures of the oldest galactic stars confirms they formed from gas that had been through at least some enrichment, but very little. They represent the early chapters of the Milky Way's stellar history. What was at the center before those stars formed? The honest answer is that we do not know directly. We cannot observe the Milky Way's first billion years of history because we are inside it, and because the relevant structures no longer exist in the form they had then. The stars that formed first have evolved and died, leaving descendants that carry their chemical heritage, but not their original form. The gas conditions of the early Milky Way are inferred from models and from the properties of surviving ancient stars, not from direct imaging. What QS01 suggests is that the standard assumption that Sagittarius A star grew gradually inside a galaxy that was already forming stars may not be the correct history for all supermassive black holes, including our own. If the primordial black hole scenario accounts for objects like QS01, and if QS01-like systems are common in the early universe rather than exceptional, then many of the supermassive black holes that now sit at the centers of mature galaxies may have formed the same way, including possibly the one at the center of our galaxy. If Sagittarius A star formed primordially, its history rewrites itself. Instead of beginning as a small black hole born from the death of one of the Milky Way's earliest massive stars, growing slowly over billions of years as the galaxy built itself around it, it would have arrived first. It would have sat at the center of a dark matter concentration in the cosmic dark ages, before a single star in the Milky Way had formed, feeding quietly on primordial hydrogen, establishing the gravitational well that would eventually become the deep center of our galaxy. The gas that produced the Milky Way's first stars fell into a potential well that the black hole had already defined. The galaxy's earliest stellar populations assembled in an environment already shaped by the gravity of Sagittarius A star. Every star the Milky Way ever formed, including the star we call the Sun, formed in a galaxy whose structure had been organized around a black hole that may have been ancient before the galaxy itself began. The Sun formed 4.5 billion years ago. If Sagittarius A star formed in the universe's first second, our star came into existence nearly 9 billion years after the anchor at the center of our galaxy. We orbit at a distance of about 26,000 light-years, a black hole that may be 13.5 billion years old. The black hole at the center of the Milky Way may be among the oldest objects in the observable universe. This is not a confirmed claim, it is a possibility opened by QS01's existence. Before QS01, the primordial black hole scenario for galactic centers was theoretical but lacked observational grounding in anything specific enough to take seriously at the level of individual nearby galaxies. After QS01, with a confirmed nearby analog showing exactly the properties the primordial scenario predicts, the question becomes less philosophical and more empirical. What tests could we run to determine whether Sagittarius A star has a primordial origin? What would we look for? What would distinguish that history from a conventional stellar collapse origin? Some of the distinguishing signatures that might survive over 13 billion years of galaxy evolution are subtle but potentially detectable. The chemical composition of the oldest stellar populations in the very innermost regions of the Milky Way could carry traces of how enriched or unenriched the gas was when those stars formed. If the black hole preceded any stellar activity in the galactic center, the very oldest central stars would have formed from particularly pristine gas, their chemical signatures sitting at the low metal extreme of any stellar population that exists today. Identifying and characterizing these ancient innermost stars requires separating them from the younger generations that dominate the central stellar population, a technically demanding task that upcoming observatories, including the extremely large telescope, are positioned to make progress on. The spatial distribution of the oldest stars in the inner galaxy also carries information. Stars that formed in the gravitational field of an already present black hole organize differently than stars that formed in a gas cloud that was independently contracting. The shapes of their orbits, the statistical patterns of their velocities, the degree to which they cluster toward the very center versus forming a more extended distribution, all encode something about the dynamical history of the environment they formed in. Detailed kinematic surveys of the oldest galactic center stellar populations, compared against simulations of both the primordial seeding and conventional formation scenarios, could in principle distinguish between them. These are long-term programs. They require instruments not yet built and observations that will take years to accumulate and analyze. But the pathway from the discovery of QS01 to tests of whether our own galaxy's center formed the same way exists, and that pathway is now being mapped. There is a broader category of question that QS01 has forced open that goes beyond any individual galaxy or any single measurement. It is a question about what cosmology is actually doing when it builds models of the early universe and what it means to confirm or update those models. The standard cosmological model, sometimes called lambda CDM for its two dominant components of a cosmological constant representing dark energy and cold dark matter, is the most precisely tested physical framework in the history of science. It accounts for the temperature distribution of the cosmic microwave background down to fractions of a degree. It predicts the large-scale structure of the universe that surveys of millions of galaxies confirm. It correctly predicts the relative abundance of hydrogen and helium produced in the first 3 minutes. The model works at a level of precision that should make anyone feel confident in its basic architecture. But every successful model in the history of physics has eventually revealed its own limits. Newtonian mechanics worked perfectly well until observations demanded general relativity. General relativity extended the description of gravity but introduced singularities that it cannot describe. Quantum mechanics explained atomic and subatomic physics, but resisted unification with general relativity for a century and counting. Every successful framework contains within it the seeds of its eventual extension, the class of phenomena that falls slightly outside its range of validity and demands something new. Lambda CDM may be reaching its own boundary conditions in the early universe. The Hubble tension, the persistent discrepancy between measurements of the universe's expansion rate from the cosmic microwave background and from observations of nearby distance indicators, has been documented across multiple independent methods and stubbornly refuses to be resolved by measurement error alone. The excess of massive early galaxies that JWST has found, more massive systems at high redshift than the standard model predicts, has been reported by multiple independent teams using different instruments. And QS01, a black hole too massive and too early for standard formation models, now adds another data point to a growing list of observations that the model handles awkwardly. None of these individually constitutes a crisis. The history of science contains many examples of apparent model violations that were eventually explained within the existing framework by more careful analysis or previously unaccounted systematics. The Hubble tension might be resolved by subtle calibration issues not yet identified. The excess of massive early galaxies might reflect insufficient modeling of baryonic physics in the simulations used to generate predictions. QS01 might be explainable by an unusually efficient conventional accretion scenario that falls within the known physics at the extreme end, but the direction in which the anomalies point is consistent. They all suggest that the early universe was more structured, more massive, more energetically active at early times than the standard model predicts. Not marginally, not at the level of noise. At levels that multiple independent teams looking at the same data have flagged as significant. If there is a systematic offset between model predictions and early universe observations, the most likely source is in the assumptions about what seeded structure in the first place. Lambda CDM treats the initial density fluctuations as coming from simple quantum noise amplified by inflation, producing a nearly scale-invariant spectrum. If the actual spectrum had enhancements at specific scales, or if additional contributors to early structure like primordial black holes were present, the predictions for early massive objects would shift upward. More massive early galaxies, more massive early black holes, more energetically active early universe. Exactly what observations are finding. This does not mean the standard model is wrong in its foundations. It means that the input conditions it uses may need refinement. The physics of inflation, the processes in the first fraction of a second that set the universe's initial state, may have been more complex or more varied than the simplest models assume. QS01 is one piece of evidence pointing toward that complexity. The scientific response to this situation is not to declare a crisis or to abandon the standard framework. It is to do more science, to measure more precisely, to simulate more carefully, to identify the specific predictions where the model and observations diverge, and to trace those divergences back to their physical origins. This is what the field is doing, and QS01 is one of the objects around which that work is now organized. The 29 hours of JWST observation that produced the most detailed spectroscopic analysis of QS01 attempted were expensive in telescope time, representing a significant fraction of a competitive observing allocation at an instrument that receives many times more observing requests than it can accommodate. The research team that secured that time had to make a compelling scientific case for why this particular object warranted that investment. The case rested on what the earlier, lower resolution data had already suggested, that QS01 was the best characterized example of a population of objects that appeared to fundamentally challenge the standard model of galaxy formation. The investment paid back in the form of the Lyman alpha spectral analysis, the identification of the clumpy neutral hydrogen structure, and the constraints on the gas distribution around the black hole that those measurements provided. These results, now available as preprints with peer review in progress, have been distributed across the astronomical community and are already being incorporated into updated theoretical models and new observing proposals targeting related objects. This is how a discovery propagates through science, not through a single decisive moment of confirmation, but through a cascade of subsequent observations and analyses, each building on the previous, narrowing the uncertainty in a different dimension, each pulling more researchers into the investigation until the question has been examined from every available angle, and the remaining uncertainty is small enough to be characterized precisely. QS01 has initiated that cascade. It is now moving through the community faster than any single team can follow, being analyzed, extended, and challenged by researchers around the world who have access to the same public data. The pace of this propagation has accelerated dramatically over the past decade with the shift toward preprint publication. When major results like the 29-hour spectroscopic campaign are made available as preprints before peer review, the community can engage with them immediately rather than waiting 6 to 12 months for the formal publication process to complete. Independent teams can run their own analyses on publicly available spectral data. Theoretical groups can update their models in response to new constraints without waiting for the official stamp of peer review. The scientific conversation moves faster, and the errors that peer review is designed to catch are often identified by the broader community engaging with preprints before the formal process completes. This speed comes with a calibration requirement. Results at the preprint stage carry less formal weight than fully reviewed publications. They should be treated as serious scientific contributions while being held to a slightly higher standard of skepticism than results that have been through independent expert review. For QS01, the earlier mass measurement and the basic characterization of the object have been through full peer review and carry that weight. The specific results from the 29-hour campaign are preprint stage results, compelling and grounded in real data, but pending the additional layer of scrutiny that formal review provides. Holding both of these in mind simultaneously, taking the discovery seriously, while maintaining appropriate calibration about what is fully established versus what is still being assessed, is the intellectually honest position. It is also, frankly, the most interesting position. The question is live, the evidence is accumulating, the answer is not yet in, and the answer, when it arrives, will be one of the most significant results in the history of cosmology. What makes following science at this frontier distinctly different from following science in more mature domains is exactly this combination of genuine uncertainty and concrete observational progress. We are not trying to improve the precision on a number we already know the rough value of. We are trying to determine whether the universe's origin story has a different opening than we thought, whether the very first objects that formed after the Big Bang were black holes rather than stars, whether the sequence in which the cosmos assembled itself runs in a different order than every cosmology textbook has described. If the answer comes back yes, the textbooks change, not the measurements in them, not the observed properties of the cosmic microwave background or the confirmed ages of globular clusters or the established dynamics of mature galaxy systems. But the narrative, the story the textbooks tell about what happened first and why, will require a new chapter inserted before the current chapter 1. A chapter set in the dark before any light existed, in which the universe's most extreme objects formed silently from the pure physics of primordial density and gravity, waiting in darkness for hundreds of millions of years while the rest of the cosmos organized itself around them. That chapter already exists in theoretical form. Hawking wrote it in 1971. What QS01 may be providing for the first time is the observational basis for moving it from theoretical appendix to established history, the tiny red speck behind Pandora's cluster, the light that left before Earth existed, the black hole that outweighs its own galaxy, the chemical silence of a medium that has never been touched by the interior of a star, the clumpy hydrogen that carries the fingerprint of a pristine primordial environment, the inverted mass ratio that breaks the relationship established across hundreds of mature galaxies, the growth rate that strains against the physical ceiling of what accretion physics allows. Every piece of data from this object points in the same direction. Every line of evidence converges on the same implication. Something formed before the normal sequence of cosmic events had time to run. Something massive and dark arrived at the party before the first guests appeared. Something that Hawking described half a century ago, working from pure theoretical physics with no observational anchor, that may have left its first confirmed fingerprint in the most powerful telescope humanity has ever placed in orbit. The story of how the universe began building itself is not finished. It is not even close to finished. But QS01 has added a sentence to the first paragraph that was not there before, and the sentence changes what everything that comes after it means. Before the stars there was darkness, and in the darkness, already there, already massive, already bending the cosmos around it, gravity, the oldest thing, the first thing, the thing that everything else grew around. We found it. Behind a gravitational lens, 13 billion light years away, in the background of an image pointed at something else entirely. A black hole that should not exist by the rules we thought governed everything, sitting in the middle of nowhere, surrounded by almost nothing, older than almost everything, still there, still waiting, carrying 13 billion years of history in every photon it lets escape, and now finally being read. To understand the full weight of what QS01 represents, it helps to step back and think about the problem of origins more broadly. Every field of inquiry that asks where something came from eventually arrives at a boundary, a point beyond which direct observation becomes impossible and inference from physical principles must take over. In biology, the origin of life sits at that boundary. In geology, the formation of the earliest continental crust. In physics, the Planck epoch, the first 10 to the negative 43rd of a second after the Big Bang, where quantum gravity effects make current physics inapplicable. Each of these boundaries is a place where the evidence thins out and theoretical extrapolation becomes necessary, but the boundary is not arbitrary. It is the point where our instruments and our mathematical frameworks reach their current limits. For black hole formation, the boundary has historically been set by stellar death. We observe stars. We observe stars of sufficient mass undergoing core collapse. We observe the remnants of those collapses as neutron stars and black holes. We understand the physics of the process well enough to model it in detail. This knowledge, combined with models of how these stellar mass black holes then grow through accretion and merging over cosmic time, has given us a framework for understanding where all the supermassive black holes in the centers of galaxies came from. It is a framework that connects observed processes at accessible scales to inferred outcomes at larger scales and earlier times. QS01 pushes the question back beyond that boundary. The black hole it contains is too massive, too early, and too chemically pristine to fit within a framework that starts with stellar death. The framework must be extended backward to a period before any stars existed, and extending it backward means operating in territory where direct observation is not currently possible and where theoretical reasoning from physical principles must carry more of the weight. This is not a comfortable scientific position. Physicists and astronomers prefer frameworks anchored by observation at every step, but operating at the boundary between the observable and the inferable is not unique to the QS01 problem. It is the characteristic challenge of any science that asks questions about origins. The response is not to retreat from the question, but to identify what evidence the boundary does permit and to evaluate competing theoretical proposals against that evidence as rigorously as possible. In the case of QS01, the boundary between the directly observable and the inferable sits somewhere in the Dark Ages, before the first stars formed. Everything after that boundary, the epoch of reionization, the first galaxies, the first supermassive black holes visible to Jadrist, is accessible through electromagnetic observation of some kind. Everything before it must be inferred from physical principles and from the properties of the objects that emerged from it. QS01's properties constrain the inferred history. An object this massive, this early, with this chemical signature, in this size of host galaxy, narrows down the range of viable physical scenarios for what happened before the first stars. The primordial formation scenario survives those constraints. Scenarios requiring multiple stellar generations do not. Direct collapse scenarios are theoretically possible but require specific conditions. Dark matter collapse scenarios are physically motivated but depend on particle properties we do not know. The range of viable explanations has been narrowed by the observation, even if a single definitive answer has not yet been identified. This is how science actually advances at the boundary between the observable and the inferred. Not through a single decisive experiment, but through a progressive narrowing of the viable theoretical space based on accumulating observational constraints. Each new measurement eliminates some scenarios, tightens constraints on others, and sometimes opens up possibilities that were not previously considered because the observational basis for them did not exist. QS01 has done all three of these things simultaneously. The fact that this object was found, characterized, and is now the subject of dedicated follow-up observations is itself a testament to how dramatically the capabilities of observational astronomy have advanced over the past generation. The very existence of a telescope with the sensitivity, wavelength coverage, and spatial resolution of JAST would have seemed implausibly ambitious to the astronomers who first proposed searching for objects from the first billion years of cosmic history. The engineering challenges involved in putting a 6.5-meter deployable mirror into a thermally stable orbit 1.5 million kilometers from Earth, cooling the detectors to within a few degrees of absolute zero, and maintaining the pointing stability required for spectroscopic observations of sources that appear as sub-arc-second red smudges in the field of view, are formidable enough that the telescope's successful operation has been described by those involved as one of the most complex deployments of scientific hardware in history. That investment of engineering, funding, scientific planning, and institutional coordination across multiple space agencies and decades of development has returned exactly the kind of discovery it was designed to make possible, not a confirmation of what was already expected. A genuinely new result that the existing framework cannot explain without modification. An object whose existence demands that the model be extended in a direction that reshapes the story it tells about cosmic origins. The parallel with the Hubble Space Telescope is worth drawing. When Hubble launched in 1990, one of its key science programs was measuring the distance scale of the universe well enough to pin down the Hubble constant, the rate of cosmic expansion. After correcting for the initial optics problem and years of observation, Hubble produced a measurement. But it also produced deep field images, exposures of apparently empty patches of sky held for days or weeks that revealed thousands of distant galaxies in what had appeared to be blank space. Those images revealed that the universe at early epochs contained galaxies in configurations that the models of the time had not fully anticipated. Galaxy merger rates, morphological diversity, star formation histories across cosmic time all were revised in response to what Hubble found in its deep fields. JAST is doing the same thing at earlier epochs with greater sensitivity and with spectroscopic capability that Hubble in the visible could not match. The little red dot population is JOT's first deep field surprise of this magnitude. QS01 is the best characterized individual example, and the revisions it is driving to models of the early universe are comparable in significance to what Hubble's deep fields drove to models of galaxy evolution at intermediate redshifts. The institutional story of how science incorporates results like QS01 is also worth understanding, not as an inside look at bureaucrat processes, but because it affects how quickly and how robustly the implications propagate through the field. When a paper reporting a significant anomalous result is submitted to a major journal, the review process involves sending it to 2 or 3 researchers who are qualified experts in the specific subfield. These reviewers examine the methodology, check whether the analysis is internally consistent, identify potential sources of systematic error that the authors may not have considered, and assess whether the conclusions follow from the evidence presented. They can request additional analysis, challenge specific choices in the data processing pipeline, and require the authors to address alternative explanations before the paper is accepted. This process is rigorous and slow. It typically takes months, and for high-profile results touching on fundamental cosmological questions, the review can be more intensive than average. Reviewers for a paper claiming a primordial black hole candidate will scrutinize the mass measurement methodology closely. They will check whether alternative explanations for the low metal content have been adequately considered. They will examine whether the star formation suppression could be explained by observational selection effects rather than physical processes. They will push back on every aspect of the interpretation that is not directly required by the data. The papers that emerge from this process carrying the quality of reviewed and accepted publications have survived that scrutiny. They represent the field's best current assessment of what the evidence shows and what it implies. The preprint stage results, which the community can engage with before that process completes, are the raw material that the review process will evaluate. For QS01, the earlier foundational papers are in the reviewed category. The most recent spectroscopic campaign results are still in the preprint category. Both types of result are informing how the community is thinking about the object and what it implies. For anyone outside the scientific community, trying to understand what QS01 means and how confident to be in that understanding, the relevant question is not whether the result has been fully confirmed in the sense of passing all possible future tests. No scientific result that is actively being developed is in that position. The relevant question is whether the evidence is strong enough and the existing alternative explanations weak enough to take the implication seriously. For QS01, the answer is yes. The inverted mass ratio is not a measurement artifact. The early epoch is not a calibration error. The chemical primitiveness of the surrounding medium is not a data processing issue. These are real properties of a real object, and they genuinely resist explanation within the framework the standard model provides. Taking the implications seriously means holding it provisionally, updating as new evidence arrives, and being clear about what is confirmed versus what is the current best interpretation. It does not mean treating it as settled before the full review process has run, but it also does not mean dismissing it as speculative simply because confirmation is not yet complete. The evidence is real, the anomaly is real. The implication is the current best explanation for why the anomaly exists. This calibrated approach to frontier scientific results is actually the intellectually sophisticated one. Demanding certainty before engagement with a result that is still developing is not caution. It is a failure to engage with science as it actually works, in stages, with accumulating evidence narrowing toward a conclusion rather than switching from unknown to known in a single moment. The most interesting science happens in the middle of that process, when the evidence is real, but the conclusion is still being worked out. QS01 is in that middle, and the middle is where the scientific action is. Let us close the loop on something mentioned earlier that deserves a fuller treatment: the specific observation technique that produced the most detailed data on QS01 and why the signal it generated was so unexpected. Lyman alpha emission is produced by a specific atomic transition in hydrogen. When a hydrogen atom is ionized, its electron is stripped away. When the free electron is eventually recaptured by a proton, it does not necessarily drop directly to the ground state. It may land in an excited state and then cascade down through intermediate energy levels before reaching the lowest possible energy configuration. The specific transition from the second energy level to the ground state releases a photon at a wavelength of 121 nanometers in the ultraviolet. This is Lyman alpha, and it is one of the brightest emission features in the spectra of objects that are actively ionizing surrounding hydrogen. In the early universe, during the epoch of reionization, hydrogen ionization was happening everywhere. The ultraviolet radiation from the first stars and from active galactic nuclei was stripping electrons from the neutral hydrogen fog that permeated the space between galaxies. Lyman alpha photons were being produced in enormous quantities as that ionized hydrogen recombined. Lyman alpha emission is therefore a primary tracer of where ionizing radiation was active in the early universe, a bright diagnostic line that tells astronomers about the interplay between radiation sources and the surrounding neutral gas. By the time QS01's Lyman alpha photons reach us, cosmic expansion has stretched the wavelength from 121 nanometers deep in the ultraviolet to about 850 nanometers in the near-infrared. This stretching, the direct consequence of the universe expanding by a factor of roughly 8 since QS01's light was emitted, is what JOSD's infrared-optimized instruments are specifically designed to detect. The telescope was built with exactly this kind of high redshift Lyman alpha observation in mind. The distorted profile that the 29-hour observation revealed was unexpected, because most models of early galactic systems predict a Lyman alpha emission profile that, while complex, follows patterns that have been characterized in other high redshift objects. A strongly asymmetric profile with one side significantly less redshifted than predicted is a specific signature associated with resonance scattering inside dense neutral gas. The light is bouncing around inside the system rather than escaping cleanly, and the specific pattern of the bounce signature tells researchers about the spatial distribution and density of the neutral material. The most striking aspect of the clumpy gas interpretation is what it implies about the conditions around this black hole at this particular moment in cosmic history. Reionization was ongoing, the black hole was actively feeding, the surrounding galaxy was barely assembled. Into this environment, clumps of dense neutral hydrogen were sitting in irregular patches around the central system, some thick enough to heavily scatter outgoing ultraviolet photons, some thin enough to let them through with minimal interaction. The patchwork structure is exactly what you would expect if the surrounding material was primordial infalling gas, not yet processed or organized by extended stellar activity, falling into the gravitational well from the surrounding intergalactic medium in the clumpy filamentary patterns that large-scale structure simulations predict for that epoch. Seeing that structure directly through its imprint on the spectral profile of the Lyman alpha emission is exactly the kind of result that validates the investment in 29 hours of dedicated observation. It is not a measurement that confirms the primordial origin of the black hole, but it adds a layer of environmental characterization that is uniquely consistent with that origin and that constrains the range of viable formation models. Each new measurement of this kind is a thread. Individually, no single thread establishes anything definitive, but as they accumulate, each independently pointing in the same direction, the picture they collectively weave becomes clearer and more resistant to alternative interpretation. This is how the confidence in a scientific conclusion builds. Not through a single decisive experiment, but through the progressive accumulation of independent evidence that all requires the same explanation. The thread count for QS01's prestellar origin is growing. It will continue to grow as follow-up observations accumulate, as independent teams analyze the existing data from different theoretical perspectives, and as new members of the little red dot population are characterized at sufficient resolution to permit comparison with QS01. The conclusion the threads are converging toward is one of the most profound in the history of the discipline. The universe's first significant structures were not stars, they were not gas clouds, they were not even the first galaxies, they were black holes, formed in darkness before any light source existed from the pure physics of primordial density and gravity. They organized the matter that followed, they determined where the first stars formed and how many. They limited how large the first galaxies could grow. They set the template for the M-sigma relation that mature galaxies would later reflect. They were, in the most literal sense, the foundation on which everything else was built. The stars are beautiful. The galaxies are magnificent. The cosmic web is one of the most intricate, large-scale structures in nature. But beneath all of it, older than all of it, in the darkness before any of it existed, the black holes. Silent, invisible, enormous, waiting for the cosmos to come to them. QS01 let us see the moment before the cosmos arrived. The black hole still dominant, still waiting, the galaxy barely begun, the chemistry not yet written, the stars not yet formed. A window onto the universe's actual first chapter, found in a tiny red pixel at the edge of everything we can see, carrying light that left before our planet, was a thought in the cosmos's future. 13 billion light years, 700 million years after the beginning of time. A black hole heavier than 50 million suns, surrounded by almost nothing, waiting in the early universe for the galaxy that would slowly, inadequately, only partially, grow around it. We were not supposed to be able to see this far back. We were not supposed to find something this impossible this early. The model did not predict it, the timeline did not allow it. The relationship between black holes and galaxies was supposed to be settled. And then the telescope found a red dot, and everything changed.